Hello and welcome to Chapter 2, Networks in Our Daily Lives from the Networking Essentials course in the Cisco Networking Academy. Today we're going to talk about how networks affect our daily lives. In particular, after this chapter is over, you should be able to list the basic requirements for getting online, explain the importance of network representations or network icons can be used in documentation and an understanding of networks, and in the end, build an Ethernet cable to be used to connect a computer or a host to a network. Most people today get onto the internet from their phones 99% of the time. Now, I say most because our phones are constantly in our pockets and they're connected to our LTE networks, 4G, 3G, and they allow us to get onto the internet. Now, I know most of our time may be spent using a regular computer, but for overall connectivity, our phones allow us to have the greatest amount of connectivity. We use different types of networks when we use our phones, and it has gone from 2G to 3G to 4G, and these are different generations. And these different generations have all been able to support different data rates. These data rates have increased consistently, and you'll notice with these devices, the number of devices using 2G has declined and will continue to decline. The number using 4G or faster will continue to increase. As I mentioned in my lecture on Chapter 1 of this course, many times at my own house, it's faster for me to turn on the wireless hotspot on my phone and use the 4G network to connect to the internet than it is to use my DSL connection. That's a sad state of affairs, but it's the truth about internet connectivity in the United States at this point. If you live in rural areas, many times the wired connections you can get are slower than the 4G connections you can get with your phone. Different types of networks allow us to connect and access different things. For instance, most of our phones have a GPS system in them. Our cars have GPS systems in them. I have a bicycle computer that has GPS systems in it. These systems connect to global satellites, project signals down to the earth, and they can be used to actually find your position within about 10 meters. This is how location services, along with their different methods using the cell towers and also using Wi-Fi connectivity that can be used for your location services on your phone. But for actual just navigation, many times the GPS system is what is used. Wi-Fi is the typical, we call Wi-Fi or Wi-Fi. It allows us to connect to either a network at our work, school, or an open hotspot. Please be aware anytime you are connected to a Wi-Fi network that is open, all of your data is sent in clear text unless it's encrypted with some type of technology such as SSL or other technologies. Just be aware there's a danger anytime you're on an open Wi-Fi connection of your information being stolen. We have Bluetooth. Bluetooth allows us to connect to our cars. It allows us to connect to any type of Bluetooth device that may be connected. For instance, Bluetooth is used on my power meter on my cycling computer to connect a power meter to my cycling computer. And then we have a new technology that's been around for a while, but it's being used more and more, called NFC, or Near Field Communications. Here at the school I work at, we actually have drink machines where you can take your phone with NFC, put it up against a pay point, and then you can buy a drink from the drink machine, from the soda machine, using Near Field Communications. This is also what's being used with Apple Pay and for Android Pay, those types of items that you can use your phone to pay using Near Field Communications. Very short range on Near Field Communications. So let's talk about the parts of a network. Again, we go back to their end devices, their intermediate devices, and then there are those devices that provide and receive services. So those are clients and servers. Hosts are any devices that are connected to the network media. So we look here and we see these hosts such as a laptop, a server, a network printer. And you'll see the network printer can play the part of two different things. It can be a host if it's directly connected to the network via a network interface card. And by the way, a network interface card is a physical card that is used to connect to the media or medium that's used on a network. Again, it can be a wireless NIC, wireless network interface card, so it'll be connecting to the medium, the RF signals, or it can be a wired NIC and it will be connected to the media, such as unshielded twisted pair that we will talk about later in this chapter. But those hosts are a host directly connected to the network via some type of media or medium. Peripherals are devices connected to hosts. They do not directly communicate on the network. They are going through a device, such as this microphone and web camera that you're receiving this recording from, or that I'm actually providing this recording through. That is a peripheral connected to my computer. A local printer connected to a PC or a scanner connected to a PC. Those are also peripherals. Network devices. Those are intermediary devices or intermediate devices. Those are the devices that are on the network and actually provide network connectivity onto the network and between different devices on the network. Routers, switches, wireless access points. Those items are all network devices. And then last but not least, we have the media or the medium, and that's the actual equipment or cabling. It's not equipment, it's the cabling that your data moves across on the network. So here's different components. Network media, well, that would have to be right here, the LAN media. Peripherals would be those devices connected to a host. A host would be any of those devices that are connected directly to the network, such as these. And then the switch is the only network device being shown in this particular drag and drop. So, connecting end devices. So how does a host device or a end device, how does it communicate on a modern network? Well, I mentioned to you in earlier chapters too that you really need three major things to have a network. Something to share, a media or medium to travel across, and then you have to have a protocol, a way to communicate. On modern networks, that protocol is called TCP/IP, Transmission Control Protocol, Internet Protocol. Each device on a TCP/IP network has an IP address and a subnet mask assigned to it. And I mentioned to you that is similar to a phone number or something similar like a phone number or an address that you can use. And then there's a default gateway that will let you get out of your network. Now, we have a lab that's coming up. You see here that's the IP address identifies the host. The subnet mask is actually used to mathematically determine what network or subnetwork a host is on. And the default gateway is basically an IP address that a host goes to if it needs to leave its network. So, I want to show you this picture. We're going to be building off of this right here. This is a lab found in the CCNA curriculum. But we're going to talk about PCA. PCA is a host on an TCP/IP network connected to the router R1. R1 has an IP address assigned to gig 01. So in order for PCA to go out of this network and go out to the internet, PCA must have a default gateway set. It also has to have an IP address assigned to it, either assigned statically or dynamically. So, the two different ways you can do IP address assignment or Internet Protocol address assignment are manual, where you go into the configuration on the device and you put in a static IP address. Now, manual and static are synonymous with one another. The other way is a concept called dynamic. With dynamic IP allocation, you set up a DHCP server. Now, DHCP stands for Dynamic Host Configuration Protocol. DHCP servers hand out IP addresses to clients or hosts that request them via the DHCP process. We will learn, and I'll show you, the DHCP consists of 4 different requests or 4 different items. A DHCP discover by the client, so a DHCP discover to discover the DHCP server. The server then sends a DHCP offer. The client will send a DHCP request, and then there will be a DHCP acknowledgement. So good old Aunt Dora, that's how I teach my students to remember it. Aunt Dora, or discover, offer, request, acknowledgement, are the 4 parts of DHCP. Now that's not really covered in this particular course, but it's something that will come up as you move forward into your CCNA training. So what I want to do here is, using this as our basis, okay, now this is the lab from Cisco, but I also use a product. And we use a product called NetLabs from a group called NetDev Group. And I'm going to go into the router. And I know it's a little small, but it's a router that is physically set up. So what NetLabs allows us to do is to have physical equipment. This is a real Cisco router, not a simulation. And then we're going to have a virtualized PC. But if I go in here and do a show IP interface brief, you will see that gigabit 01, which is this interface right here on R1, has an IP address assigned of 192.168.12.1, and it's up. I can also show you show IP DHCP bindings. It helps if you spell it correctly. Show DHCP bindings, or binding. You can see here I have a host at 192.168.12.101 with this MAC address, and this is the physical address of the network interface card, that is using the DHCP server. So I'm going to go over now and pull over the PC, and I have to pull it up just a little bit here so you can see this. I'm going to run CMD, which gives me my command line, type ipconfig. You're going to see the IP address of this machine is 192.168.12.101. The same address that's being shown as being used from the DHCP pool. So I've set up router R1 to be a DHCP server. You'll see too that the default gateway is set to 12.1 and that the subnet mask is 255.255.255.0. If I do an ipconfig/all, you will see that on this particular PC, I do have an IP address of 12.101. You will also see that it was assigned from the DHCP server 192.168.12.1, which is our router 1. Okay, and you will see that my default gateway is 12.1, and I did set a DNS server of 8888, which is one of the Google servers. Now, I'm going to do an ipconfig/release here in just a second, but I want to show you this first. I want to show you show IP DHCP statistics. And you can always use the question mark. Helps when you actually show the right thing here. So, do our pool. Here's my pool that I set up. I have 100 addresses. I have 100 addresses excluded, not shown here, but I've got the entire range of 12.1 to 12.254. If I do a show run, I can actually show you that inside of here, I excluded the addresses 12.1 to 12.100. That's why my PC picked up 12.101. You also see my pool that I named NetS. It has a network of 12.0, 24-bit mask. Default router is 12.1 and DNS is set. I can also do a show IP DHCP server and then statistics. And you will see that the DHCP inform messages are 12, but you see our discover requests. These are received information from a DHCP client and then sent. I'm going to go in here and release the IP address. You'll notice now that I have no IP address. If I do an IP config, I have no IP address assigned on my Ethernet adapter. You also see if I do show these statistics that I actually received a DHCP release request. There's one request here that I did not have before. Okay, the release. And now I'm going to go in and I'm going to do an IP config. Before I did a release, I'm doing IP config/renew. I'm going to renew my DHCP address. And you should see I get 12.101. And now if I show you my statistics again, you will see that a DHCP discover, 2 of them have been received. It sent 2 offers. 2 requests have been received. And it's replied. So you got acknowledgement. So 15 acknowledgements. So the DHCP server is sending DHCP offers out to this client. So this is a client, and now I could ping my default gateway, ping 192.168.12.1, and that replies. This is a PC that now has a dynamically assigned IP address. And if I go in the control panel, and this is a Windows 7 box, so a little different than what's shown in the lab for the chapter, but same concept, because when you get in here to TCP/IP version 4, you will see that this machine is set to obtain an IP address automatically. Now, if I wanted to give it a static IP address, I would simply click here, and this is why I reserved those first, or excluded those first 100 addresses. I can now give it 1210, and I don't have to worry about any other machine having 1210, because I reserved or excluded the first 100 addresses in the range, so the DHCP server will not hand those out. So now that I've done this, if I go in and do an IP config, you'll see my IP address is now 12.10, and I have a statically assigned. If I do an IP config /all, you'll see there's no DHCP server listed here for IPv4. And so I've statically assigned this machine now. And you can move right back. Again, here we've got static assignment. If you do obtain IP address automatically, obtain DNS automatically, you now have set it back to do dynamic allocation. And you'll notice, because of the way it's set up, if the IP address is available that it requested before, it will actually get that IP address again, 12.101. So that is pretty much obtaining an IP address via either static or manual configuration and dynamic configuration. It's very important that you're able to do this, because if you ever have a problem with your PC not being able to get on the internet, one of the first things you can check is just go and check and see if you have an IP address assigned. Now, one of the interesting things you'll see sometimes is a 169.254 IP address. This occurs when you have an instance of the DHCP server not being available. So what I'm going to do here, I'll actually give you an example of this. I'm going to config T. I'm going to go into interface gig 01, which is the interface that's connected to this PC. And I'm going to shut it down. Then I'm going to do an IP config /release, or release my IP address, an IP config /renew. And those are the commands needed to release and renew an IP address, by the way, of a dynamic IP address. This will eventually time out, and when it does, you will get an IP address of 169.254.0.0. That is what is called an APIPA, or an automatic private IP address. Windows operating systems assign themselves an address in the 169.254.0.0 network, and those addresses are not routable over the internet. And if you ever find your PC has that, typically you've got a connectivity problem with your DHCP server, or your DHCP server, that dynamic server, is not handing out IP addresses correctly. We'll come back and look at that in a second. I'll show you that 169 number. So, device names. Many times we name our devices with a workstation name. They are dependent upon your company's standards. It is helpful, very helpful, to name your devices something similar to the physical location of where the device is at. So that if you look for C209-01, you know that's PC 01 in room 209. Greatly helps with troubleshooting. All right. So now, look at these network representations. You will notice in the very lab that I showed you, here are some network representations. In other words, I was able to immediately know that this was a router because I know the symbol for a router is this. Likewise, end devices show up as these devices in most Cisco documentation, and honestly in most network documentation these days. I was also able to know that these were switches because of the fact that I've learned these different network topology representations. It's also helpful when I draw out networks to use these standard symbols so that people who see my network drawings can understand it. So this is a router, firewall, multi-layer switch. That is a switch that can also do routing functions. We have wireless media, LAN media, and the WAN media is shown using this lightning bolt symbol. Good. Commit these to memory so that you'll have them. Here's a logical information. This is showing you how the network is set up. This is actually the physical topology of the network. And many times the physical topology of a network, the way the cables are laid out, do not necessarily match the logical topology. So the logical topology is how the IP addresses are assigned and how the networks are connected and in a logical way with the IP addressing schemes. The physical topology is how the cables are physically laid out. So you see here, this is an Ethernet switch going to here, and all this. So all of this, the admin office, and all of these off of this one port here could be one subnet or one network, and all of the devices off of this could be a different network. Okay, so we basically see here that we've got classrooms as shown here, and then we've got a second logical section that are the administrative sections. And so physically, you've got multiple switches on the classroom side and multiple switches on the admin side. But from a logical standpoint, it's only seen as two different networks, a 192.168.2.0 network and a 192.168.1.0 network. So what do we mean by network media? Well, we've got a couple that we can work with. Copper cabling, all right, so copper wires within cables. Fiber optic, which is typically glass, and they say plastic fibers, but most fiber optic cable now is just glass. And then we have wireless. So how do we decide which one of these to use? Well, it really comes down to how much do we want to spend? Where do we need the connection to occur? In other words, is it going to be between buildings where there's a possibility of lightning strikes? Well, then you do not want to run copper cabling because copper conducts electricity very well. How far does it need to be run? How secure does it need to be? Because each one of these different types of cabling has a different set of parameters that are particular to them. So the most common type is copper cabling. And we have twisted pair cabling, which is a set of 4 pairs, 8 wires, not for data cabling anyway. Each one you'll notice has a slightly different twist rate. This is to allow to reduce what is called crosstalk or interference between wire pairs. You've got some interference regardless. You also know that UTP is not extremely resistant to EMI or electromagnetic interference. We have coaxial cable found more in our cable TV and our satellite TV. And then this fiber optic cable, which is cable that is glass or plastic, again typically glass now, that can go very long distances and is completely resistant to EMI or electromagnetic interference. However, it's very expensive and it's more fiddly to work with. So here's twisted pair cabling. It can be affected by EMI. In other words, here's how it works. You've got a voltage over time that determines whether there's a 1 or a 0. If there's an interference signal, that can interfere with the actual pure digital signal and change the output. Now there are some error correction methods at upper layers that would take care of this, but it's an issue that you need to be aware of, that if you need to be resistant to EMI, or if you need to go very long runs between devices, twisted pair cabling may not be your best bet. However, twisted pair cabling is our most common type of cabling because it's cheap, it's easy to work with, and it works in most cases. So here's our unshielded twisted pair. This would be twisted pair cabling that does not have shielding around each wire pair. We do have, that's unshielded. We do have shielded twisted pair cabling that has shielding around each wire pair. There are different types of twisted pair cabling called categories, and these categories support different speeds. So Cat5e supports what we call 1,000 megabits per second, if you remember our chart from Chapter 1 on speeds or on bandwidth, up to Cat7, which with screen or shielded twisted pair can do 10 gigabits per second. And then Cat6 and 6a, all of these are different categories. Now, these types typically for data cables use what is called an RJ45, which is this connector on the right. It allows for the 4-pair 8 wires to be placed into a plug and then used to connect to our network devices such as network interface cards. This RJ11 is a connector used on phone lines, and it supports 2 pairs or 4 wires. Not used in data cabling really for data networks. Now what about coaxial? Well, coaxial has a BNC connector or some type of connector that we have either BNC or F series. This is an F series. It has a braided shield, so it is a little more resistant to EMI than pure unshielded twisted pair cabling. Has an insulator, some type of plastic, which does also help protect against EMI. And then it has this conductor core, or the copper core, which can be stranded or it can be solid depending on what type you buy. This is used with our cable runs into our houses. It's used with our satellite, DirecTV, and other types of satellite runs into our houses. Fiber-optic cable. It is completely resistant to EMI, can go extremely long distances. However, it is more expensive and harder to work with. It also requires lasers or LEDs on the ends in order to send light pulses through. It is made up of a jacket, which is typically PVC, a strengthening material, and that strengthening material is usually Kevlar, same thing that bulletproof vests are made out of. A buffer, which is used to shield the inner cladding and the inner core from damage. There's a cladding that's made from a slightly different material than the core, and its goal is to help reflect light back into the core so that light will not pass what's called the index of refraction. It won't actually go out of the core, but will stay in the core as it travels along the fiber optic cable. And then the core, which is typically glass, and it is used where the light pulses actually go through the cable. Now, fiber optic cable, literally, there's no limit to the bandwidth of it. As far as the speed of light, it's what the devices we connect to on each side. So really physics are what are going to determine the speeds that can go across fiber optic cable. To this point, we don't have enough capability on the ends to exceed what is available on a fiber optic cable. So, do colors matter? Well, yes, they do. So when you go to build an unshielded twisted pair cable, you're going to have to set up and use a standard on each end. Now, pairs 1 and 2 and 3 and 6 are the pairs that are actually used typically, cables 1 and 2, 3 and 6 are used to send information. You'll notice the only difference between 568A and B is that you are changing the position of the white, green, green, and the white, orange, orange. We typically teach our students to use 568B, white, orange, orange, white, green, blue, green, white, brown, brown. Some places use 568A. The key is, if you want a straight through cable, you've got to use the exact same thing on both sides. You also need to buy your patch panels and other items in your network to match the standard that you're going to use. Here's a great example of what's being used. Transmit is 1 and 2, and receive is 3 and 6. So 1 and 2 on this side, okay, is receive 1 and 2 on this side, 3, 6. So those are the main wires being used for a standard communication across unshielded twisted pair cable. Now, the last lab in this section is to build a crossover cable. Now, crossover cable has you build one end terminated as 568A and one end as 568B. I'm not going to show you an example of this. Your instructor can do that, but you also can go out on the internet and simply search on YouTube for videos on how to create an unshielded twisted pair cabling. Before we leave, let's go back and let's take a look, and you will see that my machine that could not find, notice it said an error occurred while renewing this, unable to contact your Dhcp server. So you could not contact the Dhcp server, so my machine gave itself a 169.254.XX, some number, IP address, and this is the APIPA, or Automatic Private IP Addressing, found within within Microsoft operating systems. I hope this Chapter 2 lecture has been helpful. If you have any questions, please post them in the video below, or ask your instructor.